Hey everyone, welcome to the final episode of our neural network series. We've broken down RNNs, encoders, and decoders using engaging visual explanations. If you haven't seen them yet, I encourage you to watch them. Today, we're diving deep into the transformer, which is a deep learning model used to process and generate sequences, like text or speech. It's the backbone of machine translation, chatbots and virtual assistants, large language models, like ChatGPT, text summarization, image captioning, and speech recognition. In this example, we'll see how a transformer translates a sentence step by step. We want to translate "Eu scriu un esseu interesant" in Romanian into "I am writing an interesting essay" in English. If you enjoy this kind of presentation, you can buy me a coffee. This way, I'll be motivated to create more. The transformer's encoder typically has 6 identical layers, but we can generalize to n layers. Each layer processes the phrase to create a rich contextual representation. Our phrase goes through these steps. 1. Tokenization and embedding. What happens? The phrase "Eu scriu un esseu interesant" in Romanian is split into tokens. Eu scriu un esseu interesant. Each token is converted into a numeric vector, embedding. Then, we add positional encoding. Each word gets a position tag. The sentence is processed completely, layer by layer, from layer 1 to 6, resulting in a matrix like encoder output as incident to eu, scriu, un, esseu, interesant. H means hidden state. This matrix remains fixed and is reused by every layer of the decoder from layers 1 to 6, at every generation step, token by token. Each encoder layer has 2 sublayers, multi-head self-attention and feed-forward neural network. Let's break them down layer by layer. For each token, we apply self-attention. Every word looks at every other word. It decides which words should I pay more attention to. Example, the word interessant might pay more attention to esseu, because they are semantically related. This happens in parallel across multiple heads. This process is also called multi-head self-attention, allows each word to talk to all others to understand context. For example, scriu checks its relationship with esseu and interessant. For each token, for example, screw, 3 vectors are created: query, key, and value, by multiplying the embedding with learned matrices. Query Q is a vector representing an element, asking how relevant other elements are to it. Key is a vector for each element, used to measure compatibility with the query, like a label. Value V is a vector containing the actual information of each element, weighted by attention scores. An attention score, Q or K, is calculated to measure how relevant each word is to another. For example, screw has a high score with isu because they're closely related. Scores are normalized via softmax and used to weigh the value vectors, creating a contextual representation for each word. Multi-head attention results are concatenated. In the output we have a new matrix of vectors, where screw now includes information about its relationship with isu and interessant. Then it's passed through a feed-forward neural network, which processes each token individually to refine its representation. Each vector passes through a simple neural network, 2 linear layers with a ReLU activation between them. In the video Can GPT Think?, I explained how these 2 linear layers work, with a ReLU activation in between. Normalization is used for stability. The attention output is combined with the input via a residual connection, added, and normalized via layer normalization. The output presents a more refined vectors for each token. This whole process is repeated until the last layer. With every new layer, the representation grows richer. In layer 1, the word essay barely notices interesting. By layer 3, their connection becomes clearer. By layer 6, the entire sentence forms a crystal clear representation. Each word perfectly understands its role in relationships. The deeper you go, the smarter it gets. The final encoder output is a matrix of vectors encoding eu scriu, un isu, interessant, with its full context. Let's move on to the decoder architecture. The encoder has processed the entire sentence in Romanian. Eu scriu un isu, interessant. We now have the encoder outputs ready, contextual vectors for each source word. The decoder works autoregressively. At each step, it receives as input everything it has generated so far. The decoder starts with the special token defined in the model's vocabulary and generates one word at a time, for example, I, then am, etc. This token is unique and serves as the first signal for generation.
Once converted into an embedding, start becomes a learned numerical vector. Positional encoding is added. A vector is added to indicate its position 1, since it's the first element in the output sequence. This process, tokenization plus embedding plus positional encoding, occurs before the input goes into the first decoder layer, not inside it. What does the first decoder layer receive? The first autoregressive generation step begins once the start token is processed. In layer 1 of decoder, the sublayer masked self-attention only looks at start because it's the only token so far. The sublayer cross-attention attends to the encoder and decides what's relevant from the sentence Eu escrevo essay interessante. The sublayer feed-forward processes the result. Let's break down all these sublayers one by one. Masked self-attention. Simple analogy. Imagine you're translating a sentence word by word in real time. You have the full source sentence in front of you. Encoder output. You're allowed to look at it any time, but you must generate the translation step by step, without knowing the future translated words. That's what the mask does. It prevents you from seeing the words you haven't generated yet, ensures the decoder only sees words generated so far, to avoid cheating. For example, when generating am, it doesn't see writing. How does it work? Like the encoder, each word generates query, key, and value. A mask is used to ignore future words. For example, I can only interact with start, not am, or writing. Attention scores are calculated only for visible words, creating a contextual representation of the generated sequence. Sublayer cross-attention attends to the encoder outputs and decides what's relevant from the sentence Eu escrevo essay interessante. If the input is only start, cross-attention aligns that token with the whole input sentence. For example, gives AU a high weight because I is its translation. Cross-attention uses the entire output of the encoder, which is a contextual matrix containing representations of all tokens in the input sentence. AU, screw, essay interessante. Cross-attention doesn't pick just AU in order to translate intro I, but uses the entire encoder output matrix, assigning different weights to each token based on context.
The decoder asks the encoder, which part of the input sentence helps me choose the next word? It uses query from the decoder, keys and values from the encoder to focus on the most relevant meaning from the input. Cross-attention computes attention scores between Q from the decoder and K from the encoder to determine which input tokens are relevant. For example, when generating I, cross-attention will give more weight to YU, its translation, but also consider SCREU or SAU for added context. It doesn't focus only on YU. It analyzes the entire source sentence. Feedforward processes each token individually to refine its representation. What happens in the second layer? We are still in the first generation step. Output of layer 1 passed to layer 2. Layer 2 repeats the process on start, refining again. The output from layer 6 is passed through linear plus softmax. The model predicts the most likely next word, I. Important. In this step, only start has an embedding plus positional encoding. The word I does not have a positional encoding yet because it's not part of the input. It's just a prediction, output. Now we are in the second generation step, and we have our sequence with start and I tokens. The decoder is autoregressive. It takes into account the previously generated output as input for the next step, while also attending to the output of the encoder, which contains the processed information from the input via the encoder stack. In other words, after the model generates the word I, this word is added to the input sequence for the next step. Given a new embedding, using the decoder's embedding matrix, assigned a positional encoding corresponding to its position in the sequence, then it is processed again through all 6 decoder layers, together with the previous tokens. Softmax predicts M and so on. The decoder continues generating tokens one by one, predicting, writing, and, interesting, essay, until it reaches the special end token. This marks the end of the translation process. The Romanian sentence, Eu scriu essay interessant, has now been fully translated into English as, I am writing an interesting essay. If you found this explanation helpful, don't forget to like, subscribe, and leave a comment below. Your support really motivates me to keep creating videos like this one. Thanks for watching.